What is the quantum limit in quantum magnetometry? Imagine trying to measure a tiny magnetic field so faint that it's almost impossible to detect with ordinary tools. Now, picture a sensor so sensitive it can pick up individual electron spins. That's what quantum magnetometry aims to do. But even with the most advanced quantum sensors, there's a fundamental boundary called the quantum limit. This limit is set by the very rules of quantum mechanics, which govern the behavior of particles at the smallest scales. It's like an invisible wall that tells us how precise our measurements can ever get. Quantum magnetometers often use quantum systems such as atomic spins or special defects in diamonds, known as nitrogen-vacancy centers. These systems are incredibly sensitive to magnetic fields, making them perfect for detecting extremely weak signals. But when we try to push the sensitivity further, quantum mechanics steps in. The Heisenberg uncertainty principle states that certain pairs of properties, like position and momentum or phase and number, cannot both be measured exactly at the same time. This creates a natural noise floor for measurements. This noise is called quantum backaction. When we measure the magnetic field, the act of measurement disturbs the quantum system, limiting how accurately we can determine the field. The quantum limit is the point where this disturbance balances out with the measurement sensitivity. It's like trying to listen to a whisper in a noisy room. There's a point where noise prevents you from hearing anything clearer. Scientists describe these limits through different frameworks. The standard quantum limit is the basic boundary for measurements using ordinary quantum states. It reflects a trade-off. The more precisely you try to measure, the more you disturb the system. The Heisenberg limit is a more advanced boundary that can be reached with special quantum states and entanglement, allowing for even finer measurements. The energy resolution limit combines factors like the size of the sensor, how fast it can measure, and the volume it covers. It shows a universal quantum boundary that many sensors approach but haven't yet surpassed. Understanding these limits helps scientists design better quantum magnetometers. They optimize factors like coherence time, the length of time the quantum system can maintain its state, and measurement protocols to get as close as possible to the quantum boundary. This is important for many applications, like mapping brain activity by detecting tiny magnetic signals, studying magnetic properties of materials, or even controlling quantum computers. In essence, the quantum limit in quantum magnetometry is the ultimate boundary set by nature itself. It guides how we develop sensors and pushes us to find clever ways to get the most precise measurements possible within the rules of quantum physics.